In the last video we defined the symmetric group on n letters, which we wrote as Sn, like this, to be the set of all permutations of the set 1, 2, 3 up to n. So the set of all bijections from 1, 2, 3 up to n to itself. We also introduced some notation for elements of Sn, which was this two-row notation at the top here, the two-row notation for a function f from the set 1, 2, 3 up to n to the set 1, 2, 3 up to n was two rows of numbers where on the top you wrote 1, 2, 3 up to n, and beneath 1 you wrote f of 1, beneath 2 you wrote f of 2, and so on. In this video we're going to give a sketch proof of a theorem telling us how many permutations there are of the set 1, 2, 3 up to n. And the theorem says that the size of Sn is n factorial. So you'll remember that n factorial means n times n minus 1 times n minus 2 all the way down to times 2 times 1. So before we get into our sketch proof, let's just convince ourselves that this seems plausible by looking at an example, say n equals 2. So to think about how many permutations there are of the set 1, 2, we're just going to think about what the possible bottom rows of a two-row notation for a permutation in S2 would look like. And at the end of the last video we made the observation that what you have on the bottom row of the two-row notation for an element of Sn is the numbers 1 up to n in some order. So for S2, let's just make ourselves some space here to write some things down. In S2, the possible bottom rows, well, you've got to have 1 and 2 in some order. So the only possible bottom rows are 1, 2 or 2, 1. Right, so there's just two possibilities. That's 2 factorial, so that looks good. And for S3, the possible bottom rows for the two-row notation of a permutation of the set 1, 2, 3 are the different ways to write the numbers 1, 2, 3 in some order. So this time the possible bottom rows are, we could have 1, 2, 3, or we could have 1, 3, 2, or we could have 2, 1, 3, or 2, 3, 1, or 3, 1, 2, or 3, 2, 1. But I think we can convince ourselves that those are the only possible ways to order the numbers 1, 2, and 3. And you can see that there's 6 of them, and 6 is 3 factorial, because 3 factorial is 3 times 2 times 1 is 6. So things are looking good. It does look like our theorem is correct. So what I'm now going to do is give a sketch of a proof of this theorem. If you'd like to see a more detailed proof, a different proof, then you can find that in the online notes for 0005. But let's now just try doing a proof of this, or rather a sketch of a proof of this. And the sketch of the proof goes to think, well, first of all, the number of elements in Sn is the number of possible bottom rows of the two-row notation for an element of Sn, because a function is completely determined by what its two-row notation is. And as we just said, the bottom row of the two-row notation of a permutation is the numbers 1, 2, 3 up to n in some order. So what we need to count is just the number of ways to order the numbers 1, 2, 3 up to n. But if you think about this order, well, the thing that goes first in this order is f of 1, and f of 1 could be any of n different things. So we have n choices for f of 1. So f is my permutation in Sn. And if we then think about f of 2, well, f is a permutation. It must be a one-to-one function. So f of 1 can't be equal to f of 2, or rather f of 2 can't be equal to f of 1, because f is supposed to be one-to-one. But it can be any of the other n minus 1 numbers. So n minus 1 choices exist for f of 2 as f is one-to-one, so f of 2 can't be equal to f of 1. Okay, but the same reasoning applies to f of 3. F of 3 can't be equal to f of 1 and f of 2 because f of f is supposed to be 1 to 1. So f of 3 can be anything you like, except that it can't be equal to f of 1 and f of 2. So, and so on. We can keep making this argument over and over again. And at the end, we find we've had n choices for f of 1, n minus 1 choices for f of 2, n minus 2 choices for f of 3, and so on down to 2 choices for f of n minus 1 and 1 choice for f of n, which means the total number of possibilities for f is n times n minus 1 times n minus 2 down to times 2 times 1, which is n factorial. Okay, so that's my sketch proof. It's not entirely rigorous because you have to believe some kind of principle about if you have a certain number of choices for f of 1 and a certain number of choices for f of 2, then you get the total number of choices for f by multiplying together all those numbers. But if you'd like to see a different proof, then you can find one on the type selection notes for 0005.